Welcome back, Controls Champions, to another episode of the PLC Programming Cookbook. I'm your host, John Breen, and today we're going to be taking the torch from the last video where we talked about pseudocode, and we're going to actually turn this into a real program now. So, really quick overview, we talked about the inputs of the system, the outputs of the system, the states that the system will be in, and this is particular to a certain way of programming, which we're going to get into, and then which states drive which outputs. So in this case, state 3, the extend cylinder output is on, and in state 4, the retract cylinder output is on. We'll go from state 1 to state 2 when we push the start button, from state 2 to state 3 when there's a box present, to state 4 when the cylinder is extended, that's our cylinder switch, and then back to state 2 again when the cylinder is retracted. Now, one thing I forgot to point out last time is that based on our previous example, which I want to try and keep these kind of similar so you can compare different styles of programming, there was a 2-second delay here. So I have to see this cylinder switch for 2 seconds before I can go to the next step of the sequence, or the next state in this case is the lingo we're using. The way we deal with that in this structure can be a little bit different than how we dealt with it last time. Last time, I believe we had an extra state or we had a timer right there in line. In this case, I'm going to show you something a little bit different, and it's just for variety. This is to help you see different ways to do things so you'll recognize a sequence when you see a sequence, because there are a bunch of different kinds, and this is just a kind of sequence, or at least that's how I think about it. I would call this maybe a state machine, but honestly, I'll use that term for any sequence that I ever see because it's a very similar concept. Before we actually get into Codesys and start programming it, let us just talk about a very common rung structure, because we're going to use this over and over again. So let's say I'm making a ladder diagram, and I've got my power coming in this side and my power going out that side. Probably want a coil, and quite often we will see something that looks like this. So on the top here, these are our start conditions. These are the things that make this rung active, that we're going to want to activate this coil. And I'll just give this coil a name, CR1, for control relay 1. These here are the stop conditions. And when this area is not conductive, we're going to turn this coil off. And then the reason there's a start and a stop like this is because there's a built-in latch, and that's right here. This is a latch. This rung latches itself on. So once CR1 has been turned on, we don't care about the start conditions anymore. Now we're just watching CR1 and the stop conditions. And if the stop conditions are in a stop condition state, the start conditions don't matter because this rung won't be conductive. We won't turn CR1 on. We won't energize that. So again, very, very common rung structure. We're going to use this in our sequence. So let's dive into Codesys and see what that looks like. So here's my Codesys project. This should look very familiar. If you haven't seen the last video, do watch it. I explain how we think through this process before actually doing the programming, and that whole diagram that we just went over. First, I want to point out our inputs and simulation are all the same as they have been in previous videos. So I'm not going to go over this. Just know that it's handling the inputs and outputs to make this pusher go based on our program. So this is pretending like there's a real physical system. So I'm going to ignore that, but just that's where that comes from. I also want to point out we've got some global variables that just help us stay organized and allow us to communicate with that simulation so that we're all using the same tags or variables in this case. We've got some outputs, pusher, extend, and retract. Inputs, pusher, extend, retract, box present. And I noticed that I had stuck this start push button inside this routine before. So I pulled it out of that routine, and or POU, Program Organization Unit, is the term they use in Codesys. I pulled it out of there and put it with all the rest of the inputs, just because I thought that made more sense. So if you notice that difference, really no difference in function. It's just an organizational change. Here, you'll notice I've added tags for S1, 2, 3, and 4. These are our states. We've still got ready like we had before. We've still got permissive like we had before. And we'll go through the rest in a moment. The next thing I want to point out is our general structure of the program. And this is the way I was taught way back in college. And it's maybe a little simple and old school, but I think it's a very useful concept, a very useful way to think about a program. And even if we take inputs and outputs and put them somewhere else in a program, in modern huge programs, the concept is still very real. It's just slightly different placement. So let's look at this as if it is very valid for today's large machines, because it is in its own way. This is just a nice simplified way to view it. So we've got input rungs and we've got state rungs. Notice these are sort of backwards, state 4, 3, 2. I'll talk about that in a moment. And then we've got output rungs, where we're driving the outputs that we care about. And you'll probably notice right away, a lot of this comes straight out of the diagram that we sketched out, the pseudocode that we did before. So if I pull this up again, our last page, I want to point out, extend cylinder should happen when state 3 is true. Retract cylinder should happen when state 4 is true. Extend cylinder should happen when state 3 is true. Retract cylinder should happen when state 4 is true. So very, very simple. If we wanted these on in more than one state, for example, we want push or extend to be on in state 1 and state 3, then we would just put a contact here in parallel, and that would say state 1. And that's all we'd have to do. But I don't want that, so I'm going to get rid of it. Now, working backwards, let's come back to our states. And I'm actually going to work from the bottom state rung up because, again, I've got these sort of backwards, and I'll talk about that after I talk about how we fill in a single rung. So first of all, what gets us into state 1? This is the default state. When we're not in another state, we're not in state 2, we're not in state 3, we're not in state 4, then we should be in state 1. So these are our start conditions. And then we've got that latch we talked about. And then when do we want to stop being in state 1? Well, when it gets to the next state. If we look at our diagram, state 1 goes to state 2. So once we get to state 2, that means stop being in state 1. Once we go to state 2, stop being in state 1. So that's our stop condition for this run. And you'll notice same process applies to all the rest of these. So to get to state 2, we can come from state 1 or state 4. Again, I'll pull this back up so we can look at it. To get to state 2, we can come from state 1 or state 4. If we're in state 1, we're waiting for the stop push button. If we're in state 4, we're waiting for the cylinder to be retracted. If we're in state 1, we're waiting for the start push button. If we're in state 4, we're waiting for the pusher to be retracted. By the way, I notice here I'm keeping, in this example, I'm calling it pusher instead of the cylinder that I called it in my pseudocode. This is really just me forgetting to be consistent, and hopefully it's not confusing here. But in a real project, I always sit down with whoever the mechanical designer is, and we go through all the I/O. I write it down in a spreadsheet, and I make sure all the names that I give those things are the names that mechanical engineer is also using. And I think this is a really important step. I learned it in one of my first jobs after college, and the people there were firm with that rule in teaching me, although not necessarily always in practice. But I'm going to be firm with you. This is a very good idea. Otherwise, you're going to end up getting to the end of the project, and the mechanical team is going to have one set of names, and the controls team is going to have another set of names. And this will be different in prints and different in programs and different in manuals, it becomes a big mess and a big confusion for the customer at the end of the project. And you don't want that. So don't do what I did here. Write it down in a spreadsheet or wherever and make sure you keep following that so that you don't call it pusher here and cylinder here. So, okay, brief aside, but that's important. Keep that in mind. Another thing I want to point out here is this, where we've got parallel start conditions here. So it's just like if we had a single branch for start condition, but now we've got two, and that's okay. There's nothing wrong with that. So two different start conditions. We still have our latch, state 2, state 2. And then again, we're asking ourselves, when do we want state 2 to stop? Well, when it gets to state 3. Here's that picture again. State 2 goes to state 3. Once we're in state 3, we don't want to be in state 2 anymore. Okay, pretty straightforward. State 3 comes from state 2. We're waiting for box present. I'm not going to keep flipping back to that picture, but I think you get it by now. And we want to stop state 3 when we get to state 4. So once state 4 is true, we're out of state 3. We're past it. And this system only works if we're in one state at a time. That's the intent. And then the final step here, state 4. If we're in state 3 and the pusher is extended, latch that on, and then when we get back to state 2, because we're circling around again, I will show you the picture for that, just because this is now, numbers are a little bit out of order. You would think 1, 2, 3, 4, well, what happens next? Go back to 1, but we don't go back to 1 because you only have to push that start button once. So state 4 goes back to state 2. When we're done retracting, then we go back to waiting for a box. And this just loops forever until the power goes out. In this case, of course, in a real machine, you'd have a stop button and other things as well. Other ways to get out of a sequence. So now let's ask ourselves, why are these out of order? Well, if we did these in the other order, state 1 rung being above state 2 rung, then state 1 and state 2 could be on at the same time for one scan. And that may not be a big deal for your machine, but there are some times when that is going to be a big deal because, again, we want one state to be true at a time. So let's imagine how we scan through this. Let's just say I take state 1 and put it above state 2. And we'll just look at state 1 and state 2 for now. I know that state 1 goes to state 2 when the start push button is pressed. Okay, so at that point, all of this stuff was true so that state 1 is on. And then we push the start button. Okay, now state 2 is on. But state 1 is still on also, right? So as we get down to the outputs, if we had two conflicting outputs, like maybe we wanted to extend when we're in state 1 and retract when we're in state 2, now we're confusing that poor solenoid valve. And again, for one scan cycle, the PLC, that's not going to be a deal breaker. But for some things, that would be an issue, and we don't want it to happen that way. So by doing it in the reverse order, like we talked about, now if state 1 is true, we come through here, we turn on state 2, and then immediately the next rung says, oh, we're in state 2, turn off state 1. And that way, by the time we get down in the program, this is, the computer just scans through this. It doesn't analyze all this in parallel. It's one thing at a time. By the time it gets down here, now we're only in one state. So the output rungs behave as expected. So let's come back to the top now. And this, I've got a timer here. The timer is there, and I'm using this output. I want to talk about that for a moment. We come back here, we said we want the cylinder to be extended. We want to see that input for 2 seconds before we go to state 4. There are a lot of reasons we might do that. In this case, I was doing it mostly just to make the simulation work better. You could see it got all the way there. You could see the little light turn on that says it got there, and then you could see it come back. In the real world, we might say, well, that cylinder switch isn't exactly at the end of the stroke. So maybe we want a timer for 50 milliseconds or half a second or whatever to make sure that after we see that switch, the cylinder did actually get a chance to get to the end of its stroke. Maybe that's important. Maybe it's not. I'll let that be your call for the actual application, but we may actually, in the real world, use a timer like I'm using here. So 2 seconds, you could have another state here for that 2 seconds, but that ends up being a little weird. Now you've got extra states that have to turn on the outputs. Take my word for it, it just gets a little bit messy. So the way I am proposing here to do it, and this works well, again, we talked about input rungs, state rungs, and then output rungs at the bottom. In the input rungs, I can take that raw input and make a timer, and then use the output of that timer as if it's an input. Now it's like a processed input. It's a debounced input. And now I just use that in my regular state diagram here, state machine, and it works just fine. And it's simple and easy to read. I've named this something that makes sense. T for timer pusher extended for some amount of time. You'd have to go back up here and see, oh, it's 2 seconds. But that's how this works. And I'm going to play this once for you so that you can see that this does indeed work the way we expected it to. Push the start button. This works, the way it did last time. If I give it a box, by clicking on there, it pushes the box, clears the box out. It waited 2 seconds, and then it comes back. And I can give it another box. And we can watch these states as they go through. It's going to come back, and it's going to go to the state where well, it's not going to go back to state 1 because we're not waiting for the start button. We're waiting for a box to be present. That's what state 2 is. And in a real program, I might give these different names, something that actually makes sense. So I'm not suggesting just have state 1, state 2, state 3, because it's not very well understandable by someone who doesn't have this diagram that we've made. Okay, so we've proven that this works. Box, step to the next thing, extending, step to the next thing, okay, retracting, and step back to state 2. We've proven that this works. Now, what's this good for? What's it not good for compared to other ways of sequencing? Now, this is where I give you my opinion. I think this is really good for teaching because it's a nice, concise process. Start to finish, we can make a sequence. We can understand how it works. We can talk about having to have these rungs out of order, and you will see some of that in real world. And I think it's fairly easy to understand. It's got this standard rung structure that says start conditions, latch, stop conditions. To turn this thing on, we're going step by step, 1, 2, 3. There's a lot of simplicity to it, and that's nice. I would argue, however, that this would not be good for complicated things. If you have a lot of states, this could quickly become confusing, again, if you don't have the state diagram. Or if we have this state diagram and we've got a lot of things that come back and forth like this, and that's a real world thing sometimes, like, maybe not these actual inputs, but what if we were to try something? Like state 2 is trying to do something, and then it finds out, oh, actually there wasn't a box. Maybe I need to go back to that state and try that thing again. Whatever it is. This doesn't actually work in this case. I would have to have a dummy state right there in the middle, because otherwise this structure doesn't work. And yeah, you could put a dummy state there. That's fine. That's perfectly reasonable. When I was taught this in college, the professor was convinced this was the best way to do any PLC programming. And I think that couldn't possibly be his opinion if it didn't work in the real world, because he had been in the real world before coming to school to teach us. You just have to know these little workarounds. So again, quick summary, I would argue this is good for teaching. It's good for the thought process. It's good for simple things. And it's nice to be able to diagram and structure a program like this. It's not as good for complicated things, and it's a little bit harder to do the internal documentation because you don't have this pretty diagram anymore. So, little food for thought. Feel free to use this in a simple system. It's not bad at all. I'm not trying to steer you away from real world use. It's just not where I tend to go. By the way, last thought here. This is a new whiteboard app that I'm just kind of trying out here. I'm very interested in what you think. Is this a helpful way to diagram and explain things? Do you like my dry and engineering color scheme? Are things big enough? Is my handwriting okay? Do you have any other suggestions, observations, recommendations? I'm all ears. Always trying to do this better, make it make more sense, make it more helpful. Keep that in mind. Let me know. Leave a message in the comments. Give this video a thumbs up if it was helpful. Cool. See you next time.
Thank you for amusing my American brother, John. He does so enjoy it when people watch his videos. Be a good chap. Share, like, subscribe, and comment. I'm sure he would be ecstatic to hear your impressions. Cheerio.